Okay, so we're getting to the point where we can actually work on constructing some MO diagrams. And in order to do that, we need to think about the energy of the atomic orbitals from which the molecular orbitals are being made. There's a really important principle in constructing MO diagrams, which states that you basically need atomic orbitals of the same symmetry, so they can mathematically overlap, and similar energies so that you have effective overlap. Okay? So you want similar energy and same symmetry of your atomic orbitals to make molecular orbitals. So let's look at the energy of the atomic orbitals. Um, what is an energy of an atomic orbital? Turns out that is basically the ionization energy, right? I mean, you have an electron in an orbital, and if you're to remove that electron out of that orbital, that's what the ionization energy is, okay? Might be the first ionization energy if it's an outermost orbital, or the second ionization energy or something, right? Or a third if it's an innermost molecular orbital, atomic orbital. But you can measure these things and experimentally, and you can also compute them, all right? And so what do we see here? We see that the atomic orbitals, so this is from hydrogen to neon, the first, 10 elements. The atomic orbitals decrease in energy as the atomic number increases. Why is that? Same reason ionization energy increases, right? It's essentially this is ionization energy. More positive charge pulls in the electrons more closer in, right? More attraction. So you follow any of these, you go to 2p from boron to neon, it's going down as you go across the periodic table. It's 2s. As you add more protons, going down, more and more stable, requires more energy to eject the 2s electron from neon, far more than lithium. Helium, hydrogen all the way to neon going down for the 1s. But what is interesting is the lower energy orbitals are affected more severely by this trend. So in other words, the slope of the 1s versus the 2s versus the 2p, the slope of the 1s is the greatest, and the 2s is in between. Why is this? Well, the 1s is closest to the nucleus, has the least amount of any orbital of electron shielding, right? So it's going to feel the effects of the protons of the nucleus more and more as you go across the periodic table. So these sort of guidelines in terms of the relative energies of atomic orbitals will help us when we talk about actually constructing MO diagrams, which is what we're going to do in the next video.